Welcome to the course Introduction to Mobile Robotics. In this session, we focus on one of the most important estimation tools used in robotics, the Kalman filter. In mobile robotics, we constantly deal with uncertainty. Sensors are noisy, actuators are not perfect, and the environment is unpredictable. If we depend only on sensor readings, our estimate becomes noisy and unstable. If we depend only on the motion models, errors accumulate gradually. So we need a method that intelligently combines both prediction and measurement. The Kalman filter provides exactly that. It is a mathematical framework that continuously balances what we expect to happen with what we actually observe. Under certain conditions, it gives us the best possible estimate. It is widely used in robotics, aerospace, navigation systems, and control engineering because it handles uncertainty in a systematic way. The Kalman filter works recursively. This means it updates the estimate step by step as new data arrives. It requires three main components: a mathematical model of how the system evolves, sensor measurements, knowledge about uncertainty in both model and measurements. The key principle is very intuitive. The best estimate lies somewhere between prediction and measurement. If prediction is very uncertain and measurement is reliable, we move closer to measurement. If measurement is noisy and prediction is reliable, we trust the prediction more. This balance is calculated mathematically using covariance values. So conceptually, the Kalman filter is an intelligent averaging process based on uncertainty. The Kalman filter estimates the system state. In robotics, the system may include position, velocity, orientation, and angular velocity. Instead of just estimating a value, the filter also estimates uncertainty. So, at time, every time step, we have an estimated mean and a covariance matrix. This is important because knowing uncertainty helps in decision making. If uncertainty is large, the robot knows it must rely more on sensor correction. So the Kalman filter provides not just an estimate but also a measure of how reliable the estimate is. The Kalman filter operates in two repeating stages. First is a prediction step. Here, the robot uses its motion model and control input to predict the next state. During this stage, uncertainty increases because motion is never perfectly accurate. Conceptually, the estimate moves forward and the certain uncertainty spreads. Second is the correction step. When a new sensor measurement arrives, the filter compares it with the prediction. If the measurement matches closely, only small adjustments are made. If the difference is large, the estimate shifts more significantly. After correction, uncertainty decreases because we have incorporated new information. So the cycle is predict, uncertainty increases, correct, uncertainty decreases. So the cycle is predict, so the cycle repeats continuously. The classical Kalman filter works under two main assumptions. First, the system must be linear. This means the motion model and measurement model must be expressible as linear equations. Second, the noise must follow a Gaussian distribution. When these conditions are satisfied, the Kalman filter produces the optimal estimate in the least square sense. However, many real robotic systems are non-linear. For example, robot orientation involves trigonometric functions. That limitation leads us to the extended Kalman filter, which we will discuss shortly. Let us consider a simple straight line motion example. The robot moves forward. Odometry predicts its position, but over time drift accumulates. Meanwhile, GPS gives position measurements but They fluctuate due to noise. The Kalman filter combines both. If GPS is noisy but odometry is stable for short durations, the estimate remains smooth. If odometry drifts significantly, GPS pulls the estimate back toward the correct position. The result is a trajectory that is smoother than GPS alone and more accurate than odometry alone. The sample example, this simple example captures the essence of Kalman filtering in robotics. Now we'll see the conceptual overview of the extended Kalman filter. Now let us address the limitation of linearity. Most robotic systems are non-linear. For example, motion equations involve sine and cosine. Sensor measurements may be non-linear functions of position. The extended Kalman filter or EKF extends the Kalman filter to nonlinear systems. It does this by linearizing the nonlinear functions around the current estimate. This is achieved using a first order Taylor series approximation. So at each step, the nonlinear model is approximated as linear. Then the standard Kalman update is applied. This allows us to use similar principles in nonlinear systems. So the core idea of EKV, as already discussed, it handles nonlinearity by linearizing the nonlinear model around the correct estimate and then applying the standard Kalman filter equation to the linear approximation. So we use, as already mentioned, it is done using Jacobian matrices, but for conceptual understanding, it is enough to know that EKF locally linearizes the system, as already discussed. In mobile robot localization, motion model is nonlinear due to rotation and trigonometric terms. And in measurement model, example, the range and bearing to landmarks is also nonlinear. The EKF performs nonlinear prediction using motion model, linearization of model, measurement update, and covariance update. It recursively estimates both the state and the uncertainty. Now we will just see the strength of EKF. The extended Kalman filter is widely used because it can handle nonlinear motion and measurement models. It is computationally efficient compared to particle filters. It works well in many practical robotics applications including SLAM and localization. When the system is mildly nonlinear and noise is approximately Gaussian, EKF performs very well. It offers a good balance between accuracy and computational complexity, which makes it suitable for real-time embedded systems. That is why EKF has become one of the most popular estimation techniques in robotics. Despite its popularity, the EKF has limitations because it relies on linearization. Approximation errors are introduced. If the system is highly nonlinear, these errors may become significant. Its performance also depends on good initialization. If the initial estimate is far from the true state, the filter may diverge. Additionally, it still assumes Gaussian noise. If noise distribution is very different, performance degrades. So while EKF is powerful, it is not universally optimal. To summarize the comparison, the Kalman filter works for linear system with Gaussian noise and provides optimal estimation under those assumptions. The extended Kalman filter handles nonlinear systems by linearizing them locally. KF is mathematically exact under its assumption. EKF introduces approximation but extends applicability. In robotics, because motion models are nonlinear, EKF is more commonly used. Understanding both helps us appreciate how estimation techniques evolve from ideal assumptions to practical implementations.